Hi everybody, in this video I'm going to go over two body problems. These are problems that involve two objects of interest and we're looking at the forces exerted on them. So here in the situation we have, you push two crates that have different masses on a smooth surface. M1 is greater than M2. Our goal is to determine the acceleration of the boxes and determine the force the boxes exert on each other. So we're going to look at the boxes together first. So our system is both the crates. And we're going to start out with a force diagram for just what's drawn in this picture. You push crate 1, which pushes against smaller crate 2. So we have the force the earth exerts on the boxes. And of course the normal force the ground exerts on the boxes. And then we have the force of the person on the boxes. And in this case, we're going to ignore friction because it says a smooth surface. So now we're going to write a sum of the forces statement, and we're only looking at the x or horizontal direction because that's our direction of motion. So we're going to say our sum of the forces in the x direction is our force of the person on the boxes. And we're just going to make this positive direction to make that easier for ourselves. So our Newton's second law says that acceleration is 1 over the mass times the sum of the forces. And so I'm going to put my sum of the forces in here, and I'll get the acceleration is 1 over the mass times the force of the person on the boxes. But I'm also going to change here that mass is the mass of object 1 and object 2. So I'm going to rewrite this as acceleration is 1 over m1 plus m2 times the force of the person on the boxes. Okay? All right, now we're going to look at the situation if we were to switch the position of the boxes. So now the person is pushing from this side. Okay? And we're going to see if that makes any difference. So our system is still the two boxes. And so, of course, we're still going to have the force of the earth on the boxes and the force of the ground on the boxes. But this time the force of the person on the boxes is going to be in the negative direction. Okay. So now my sum of the forces in the x direction is the same, but it's negative. So negative force person on boxes. Okay. So if I'm writing my Newton's second law equation, acceleration equals, the mass is still the mass of both objects, m1 plus m2, okay? Because our system is still both boxes. But now the sum of the forces is going to be negative force person on boxes. So what we see here is that even if we switch the direction of the boxes, the mass doesn't change because our system is still the same, and the amount of force doesn't change. So the only thing that changes is the direction of the acceleration. Okay? So based on your force diagram, should it be easier to push the crates in one situation than the other? We're going to say in that situation, no. The masses are going to be the same, so it's going to be the same. Okay? And then the acceleration is going to be the same, but just in opposite direction. Okay, so we're looking at, but a different direction. Okay, so now we're going to look at the boxes separately. So if we look back up here at our drawing, we're going to look at the boxes separately. So let's look at the system of just box 1. Okay, so box 1 for a force diagram would have the earth, the floor, the person, and also box 2. So let's make a force diagram for that. Let's have force earth on 1. I'm just going to write 1 instead of box 1. Force ground on 1. And then we have force person on 1. And then we have force 2 on 1. right? And that's because these two boxes are touching each other box 2 must exert a force on box 1. So now where some of the forces in the x direction has 2 forces. It has force person on 1 minus force 2 on 1. So our Newton's second law is going to be acceleration is 1 over, my mass is just going to be the mass of object 1, so m1. That's because that's our object of interest. Times force person on 1 minus force 2 on 1. Okay? So that's the system for box 1. Now let's look at box 2. So this time, instead of box 1, we're looking at box 2. So for box 2, we don't have the force the person exerts because they're not directly touching the box. We only have force 1 on 2, and the ground and the earth. Okay, so we have force ground on box, force earth on box, and I should have put box 2 here. And then we have force 1 on 2. Okay? So in this case, my sum of the forces is only force of box 1 on 2. So my acceleration equation is going to be 1 over m2, mass of box 2, times force 1 on 2. So now, if we think back to our Newton's third law here, we know that when objects exert forces on each other, they are equal in magnitude and opposite in direction. So this and this, these are Newton's third law pairs. So the force that 2 exerts on 1 is going to be equal to the force that 1 exerts on 2, okay? Just that this one's negative. So those things are going to be equal. So we can use that when we're solving. So now let's solve the whole thing together. I'm putting in some numbers here. We have the mass of each and we have the force. So it says using Newton's second law equation you came up with for the system of both boxes, determine the acceleration of the boxes. Okay, so we're going to come and grab this equation over here. And we're going to write acceleration is 1 over m1 plus m2 equals force, times I should say, force person on boxes. Okay, so now we're just going to plug in some numbers here and we get acceleration is 1 over 2 plus 5 times 20, which is 20 over 7, which gives you 2.85 meters per second squared. Okay. So next, you're going to use the acceleration we just found and the Newton's second law equation for box 1, right here, to determine the force that box 2 exerts on box 1. And actually, since these two are equal, you can either use the equation for box 1 or you can use the equation for box 2. And I'm actually going to go with this equation because it's a little bit simpler. You can solve using either one and you would get the same answer. But this one has less math involved. You don't have to do that subtraction. So I'm actually going to use the box 2 equation. So I have acceleration is 1 over m2 times the force of 2, I should say 1 on 2. Okay. So our acceleration we know is 2.85 equals 1 over m2 is going to be 5. And I don't know what this is, so I'm leaving it as f. So now I have to solve for f. So I'm going to multiply both sides by 5. And I get my force of 1 on 2 is going to be equal to 5 times 2.85, which is 14.28. Okay. And since we know force 1 on 2 is equal to negative force 2 on 1, that means that force 2 on 1 has to be negative 14.28, and that should be in newtons. Okay, so that's my final answer. I've calculated the forces that the boxes exert on each other using Newton's third law, and I've calculated the acceleration using Newton's second law. So now, you should be able to write a step-by-step procedure for how to solve this, and then solve this similar problem. Now let's look at a similar situation where we have two objects that are connected by a rope. Very similar. We're going to be looking at the system together and then separate. So looking at it together, all right, we have two boxes connected by a rope. And first we're going to look at the system of the two boxes together. And for that, we're going to have the force of the person over here. We're going to have the earth and the ground, okay? So I have force earth on boxes, force ground on boxes, and force person on boxes, okay? So our sum of the forces in the x direction is just going to be force person on boxes. And our acceleration would be, acceleration is 1 over, since it's both boxes are our objects of interest, it's going to be m1 plus m2 for our mass. And then times force person on boxes. Okay. Now let's look at the situation where we're only paying attention to box 1. Okay, so box 1 is obviously going to have the earth and the ground, but then the thing that's exerting a force on it is this rope. Okay, so we have force earth on 1, force ground on 1, and then we have force rope on 1, okay? And sometimes you hear that called tension. Anytime there's a string or a rope or a cable that's exerting a force, that's called a tension force. So our sum of the forces in the x direction is force rope on 1. So our acceleration equation is 1 over m1, because that's our object of interest, times force rope on 1. Okay. Then if we look at box 2, we have two forces exerted. We have the force of the person and the rope, and then of course the earth and the ground. Force earth on 2, force ground on 2, and we have the force of the person on 2, and the force of the rope on 2, okay? So our sum of the forces in the x direction is going to be the force of the person on 2 minus the force of the rope on 2. So that makes our acceleration equation 1 over m2 equals force person on 2 minus force rope on 2, okay? So now I want to bring back this idea of tension. So this force that the rope exerts is called T, tension. And it's the same thing, right? This is the same rope. So the tension force that the rope exerts on 1 and 2 have to be the same, okay? So force rope on 1 is going to be equal to the force of the rope on 2, and that's called our T, or tension force. You can abbreviate tension with a capital T. Okay, so now we're going to put in some numbers and solve. We say mass 1 is 4 kilograms, mass 2 is 6 kilograms. You pull the string with a force of 35 newtons. So using the Newton's second law equation you came up with for the system of both boxes, let's determine the acceleration. So this is the equation we're using now. Acceleration is 1 over m1 plus m2 times the force of the person on the boxes. Okay, so in this case we have m1 is 4, m2 is 6. Okay, let's try again. And then the force the person exerts is 35. Okay, so we have 35 divided by 4 plus 6 is 10, which gives us 3.5 meters per second squared. So that's going to be our acceleration. And now we're going to use the acceleration to find the force the string exerts, okay? So we're looking for the tension force, okay? So again, you can decide which one you want to use. You can either use the equation for box 1 or the equation for box 2. They're both going to give you the same answer, but I'm going to use the equation for box 1 just because it's simpler. So I'm going to have acceleration is 1 over m1 times that tension force. And again, I'm replacing force rope on 1 with T for tension. So I know my acceleration is 3.5 equals 1 over m1 is 4 times T. So now I'm trying to get T by itself. I'm going to multiply both sides by 4, and I get a tension equal to 14 newtons. So that's our tension force. Oops. And that force, again, we're using this fact here that the force the rope exerts on 1 is equal to the force the rope exerts on 2, and that's called our tension force. So it's going to be the same for both of them. Okay? So from here, you can write a step-by-step procedure on how we solve this kind with the tension, and then solve this similar problem. Okay? So the key ideas in any of these two body problems is you want to go through and look at your objects together as one system and then look at that individually. And you're going to make force diagrams, some of the forces statements and acceleration statements using Newton's second law, and then you can add in your numbers and solve from there. Thank you for listening.